in the previous video, we defined a product of two vectors called the dot product. And we looked at the vector u dotted with the vector v, and the result was a real number. Our goal today is to look at a different kind of product of vectors, and we're going to take u and we're going to take the cross product with v, and our result is actually going to be a vector. And with dot products, we saw that there was a physical interpretation. Dot products were used for projections. So with cross products, we're also going to try and find a good, valid interpretation for why we would want to take the cross product of two vectors to get another vector. So let's define the cross product of two vectors. So my two vectors are going to be u, which is equal to u1, u2, and u3, and v, which is equal to v1, v2, and v3. And the cross product is generally defined by taking the determinant of a 3 by 3 matrix. So the matrix that we're going to take the determinant of is I, j, and k in the first row. And these are supposed to represent the I, j, and k vectors that define the three-dimensional coordinate system. The second row is the vector u, u1, u2, and u3. And the third row is the vector v, v1, v2, and v3. Now there are a couple different ways that you can take the determinant of this matrix. I'm going to show you the way that we would generally define a determinant in a linear algebra class. So the way that we look at this determinant is we look at the upper left corner, which is I, and we go ahead and write that down. That's like the I hat vector. Once we have defined, or once we have looked at that upper right-hand corner, then we ignore everything in that row and then everything in that column. And so what's left is actually the determinant of a 2 by 2 matrix. That determinant is of the matrix u2, u3, v2, and v3. And we will show in a moment how to take the determinant of that matrix. But for now, you just need to know that we are going to define the 3 by 3 determinant in terms of 2 by 2 determinants. So that is the first row, or the first component. Okay, the next one is going to be minus j. So I'm now going to look at the second element of that row. I am going to put a minus sign in front of it. And then I'm going to cross out that row and cross out that column. And then I'm going to multiply it by the 2 by 2 determinant of the leftover matrix. Okay, so that's moving across the row. I've done I and then j. I go back to k. And I'm going to go ahead and cross out that row, cross out that column, and then I'm going to take the 2 by 2 determinant of what is left, u1, u2, v1, and v2. And so that's how you define a 3 by 3 determinant in terms of 2 by 2 determinants. Now this idea can actually be done with any row or any column. I could have used these 3 entries and then say crossed out this row in this column, okay, or crossed out this row or that in this column. Okay, so you can do it using any row or any column. The important part is that the coefficients that you choose, they have a pattern that goes plus, minus, plus, and then you would have minus, plus, minus, plus, minus, plus. For now, though, we really only need to compute 3 by 3 determinants for cross products. And so you're always going to use that top row with I, j, and k to expand this determinant in terms of what are called 2 by 2 determinants. Okay, now, how do we do the 2 by 2 determinants? Well, these are a little bit easier. What you do is you multiply the diagonal and then subtract the product of the other diagonal. So here we're going to do u2 v3 minus u3 v2. So if we do minus j, okay, we're going to want to multiply. Again, we're going to multiply the diagonal here and then subtract the product of the diagonal there. So it's going to be u1 v3 minus u3 v1. And then finally, we're going to finish with plus k. And we're going to get u1 v2 minus u2 v1. Again, what we have done here is we have multiplied along the diagonal and then subtracted the product of the other diagonal entries. And this is how a 2 by 2 determinant is defined, and it actually makes it consistent so that you could define 2 by 2 determinants in terms of 1 by 1 determinants using the same logic that we did for 3 by 3 determinants and defining them in terms of 2 by 2 determinants. But for now, let's just use the given formula for the 2 by 2 determinant to help us out there. And then what we want to do is we want to interpret I hat as being the 1, 0, 0 vector, so that in components, we have that the first component 1, 0, 0 is multiplied by u2 v3 minus u3 v2. Okay, so the first entry in our vector is the coefficient of the I hat vector. Okay, the second entry is actually going to be multiplying by the -1 u3 v1 minus u1 v3. And then the third component is going to be u1 v2 minus u2 v1. And so it is acceptable to either write this vector in terms of I hat, j hat, and k hat, or in terms of the components. You'll notice, because we're going to take I, j, and k, and then we're going to use the u and v vectors to form this 3 by 3 determinant, the cross product really only makes sense in 3 dimensions. Dot products make sense in any dimension, but cross products only really make sense in 3 dimensions. So what we're going to do is we're going to compute one of these cross products using or with 2 vectors. Okay, so let's look at the vector 3, -1, 2, and 2, 2, -1. So my cross product, I'll think of this as being u, and this one as being v. And so u cross v is going to be the determinant of a matrix. That matrix has entries I, j, and k, 3, -1, and 2, 2, 2, and -1. So when I take the determinant of that matrix, I'm going to get I times, notice that I'm going to cancel out the row and the column there. And so I'm left with -1, 2, 2, -1. So -1, 2, 2, -1. Then I'm going to subtract j. And here I'm going to cancel out that row and that column. What I'm left with is 3, 2, 2, -1. So So I'm left with 3, 2, 2, negative 1. And then finally, I'm going to do k. Here, I'm going to cancel out that row and that column. What I'm left with is 3, negative 1, 2, 2. 3, negative 1, 2, 2. Okay, so I'm going to get I times negative 1 times negative 1 is 1. 2 times 2 is 4, so 1 minus 4. Minus j times 3 times negative 1 is negative 3. Minus 2 times 2, so minus 4. And then plus k, and that's going to be 3 times 2, which is 6, minus a negative 2. That's negative 1 times 2. So the result is going to be negative 3i plus 7j plus 8. Okay, we could write that as negative 3, 7, 8. And that is the cross product. Now, why do we care about the cross product? Okay, let's start with the following theorem. The theorem says that the cross product of u and v is perpendicular to both u and v. So the resulting vector is actually perpendicular to both u and v. So how do you show that two vectors are perpendicular? One way to do that is to take the dot product. So actually, for the example, I'm going to show that the resulting vector of the cross product is actually perpendicular to both of the other vectors. So I'm going to do u, and I'm going to dot that with u cross v. And so I'm going to take 3, negative 1, and 2, and I'm going to dot that with negative 3, 7, and 8. Okay, this is a way that I could check my answer to see that it's correct. And so I'm going to get negative 9 minus 7 plus 16, and that's going to be 0. Then I could take v, and I could dot that with u cross v. And my vector 2, 2, and negative 1, I can dot with negative 3, 7, and 8. If I do that, 2 times negative 3 is negative 6, plus 2 times 7, which is 14, minus 1 times 8, so minus 8. And that, of course, is, again, 0. And so the resulting vector, u cross v, is actually perpendicular to both u and v. So we can actually prove this in general. We can ask if we have the cross product u and v, is it perpendicular to both u and v? So we're going to do u dotted with the vector u cross v. And we're just going to see if that is equal to 0. So if I do u and I dot it with u cross v, I'm really doing u1, u2, u3, and I'm dotting that with the resulting vector that I got from the cross product, which was u2v3 minus u3v2, u3v1 minus u1v3, and then finally u2v, u1v2 minus u2v1. So that is what I want to compute for my dot product. Put it right there. So what does that equal? Well, that equals u1 times u2v3 minus u3 v2. Okay, so that's the first component here times the first component there. Then I can do, say, the second component times the second component there. So I'm going to get u2 times u3v1 minus u1v3. And then I'm going to do the third component, u3 times the third component there. That is going to be plus u3 times u1v2 minus u2v1. So we're writing this all out. So we're going to get u1, u2, v3 minus u1. I'm going to put these in numerical order so I can get them all straight. v2, u3 plus v1, u2, u3 minus u1, u2, v3. I'm going to make that a better v there. Plus u3, nope, u1, v2, u3 minus v1, u2, u3. Okay. Now, u1, u2, v3 is the first term. And here, I can cancel that with a minus u1, u2, v3. Negative u1, v2, v3, that's the second term. I can cancel it with this positive u1, v2, u3. And then finally, v1, u2, u3 cancels with v1, u2, u3 with a negative at the end there. So in fact, we have that u dot u cross v is in fact equal to 0. Okay, so therefore, u is perpendicular to u cross v. And if you wanted to do the same thing for v, you can also do the same thing for v. So to finish this proof, we're just going to say similarly v dot u cross v is equal to 0. And v is perpendicular to u cross v. So you could do that on your own. So one context in which we can use cross products is if we have two vectors and we want to find a third vector that is perpendicular to the first two, we can use cross products to find that perpendicular vector. Okay, let's use this information to give us some other facts. Okay, let's calculate the cross products of 1, 0, 0, which is, of course, the I hat vector, 0, 1, 0, which is the j hat vector, and 0, 0, 1, which is the k hat vector. So let's ask ourselves, what is I cross j? Hopefully, you have some intuition into what I cross j is, because we need a third vector that is going to be perpendicular to both 1, 0, 0 and 0, 1, 0. Okay, and so I'm going to put the I, j, and k into my determinant, and then 1, 0, 0, 0, 1, 0. That's going to give me I times 0, 0, 1, 0 minus j times 1, 0, 0, 0, and then plus k times 1, 0, 0, 1. And so here, the determinant of 0, 0, 1, 0 is actually 0. And the determinant of 1, 0, 0, 0 is actually 0. And then finally, the determinant of 1, 0, 0, 1 is in fact 1. And so the result is that I cross j is actually equal to k. And this makes sense because we have we have I, which is pointing out towards you there. We have j, which is pointing to the left. And so we have I and j that are in the xy plane. So the only direction that could possibly be for the resulting cross product is actually k, which is pointing up, so that k is perpendicular to both I and j. So I cross j equals k. Well, now what about j cross k? What does that give me? So that's in the yz plane. What should the resulting vector be? We can, again, look at this determinant. J is, of course, 0, 1, 0, and then k is 0, 0, 1. So we're going to get I times the matrix 1, 0, 0, 1 minus j times the matrix 0, 0, 0, 1, and then plus k times the matrix 0, 1, 0, 0. And then the result, because this determinant is 1, this one is 0, and this one is 0, is that j cross k is going to give me I. So I cross j gives me k. So you do these two cross together, it gives you k. You do j and k cross together, that gives you I. Feels like that means that if I do k cross I, kind of moving around that three-dimensional coordinate system, I should get j. Let's make sure that's the case. I, j, and k. 0, 0, 1, 1, 0, 0. That's going to give me I times the matrix 0, 1, 0, 0 minus j times the matrix 0, 1, 1, 0, and then plus k times the matrix 0, 0, 1, 0. And then the first determinant is going to be 0. The second one's actually going to be -1, and the third one is going to be 0. And so we get, again, j. So I cross j is k, j cross k is I, and k cross I is j. And these three vectors actually form what we call our right-handed coordinate system. And we'll talk a little bit about right-handedness and the right-hand rule in an upcoming video. So the last thing I want to mention for this video is some properties of cross products. Okay. So, for example, U cross V, it turns out you can prove this using components, but this is actually minus V cross U. So essentially, when you exchange the two rows in that determinant, you actually get a negative sign. Okay, so this is interesting because we're used to products where the product of U and V is the same as the product of V and U. Okay, that's the property of commutivity. But in this case, U cross V is actually minus V cross U. Okay, there's a distributive property. Okay, if you have K times U, where you have that scalar constant, and then you cross that with V, that's the same thing as K times the vector U cross V. We have another distributed property here. We have U cross V plus W is the same thing as U cross V. plus V cross W. Sorry, U cross W. We can do this with dot. We have an interesting property here with dot products, which is that U dot V cross W is the same thing as U cross V dotted with W. This actually comes from a property of the determinants. And then finally, U cross V cross W actually equals U dot W times the vector V. So that's a scalar times the vector V minus U dot V times W. Now, all of these properties of cross products can be proven just by looking at the definition of the cross products, using a determinant, and then filling in what U, V, and W are. U being U1, U2, U3, and V being V1, V2, V3, W being W1, W2, and W3. So I will not prove them in this video, but they are important properties for you to use, and so I present them here.